So let's say a particle moves along the curve traced by a vector function. R of t is equal to t squared I hat plus 2tj hat plus ln t k hat. And we want to find velocity and acceleration as functions of t. So a particle moving along this curve, right, the curve traced by this vector function, this is really its position function, right? So if we think about just drawing, now I'm going to draw a little 3D grid here, and this curve isn't most likely not what is actually the path trace, because there's like a loop here, and realistically it won't look something like this. But what I'm trying to show you is that if this were the vector function r of t, then this is the curve traced out by the function, right? So at any point along its curve, r of t, this is really the this is really the position, right? This is a position vector. So this is what this function tells us. That's, it traces out a curve in space. So velocity and acceleration, they're related to the position function via derivatives, right? Because velocity, by definition, is the rate of change, the rate at which an object's position changes. So the rate at which it changes with respect to time, that's just taking the time derivative. So the velocity function v of t is really just r prime of t, and I can take this derivative pretty quickly, right? I know it's going to be to take the derivative of vector functions, we've done this before, we're just taking the derivatives of the components, and that gives us the component. So 2t I hat plus 2j hat plus 1 over t k hat. And acceleration is defined as the rate at which velocity changes, right, with respect to time. So once again, we're taking the time derivative of velocity. Now, if we've taken, to get velocity, we have to take the derivative of the position function, and we're taking the derivative of velocity to find acceleration. That means acceleration is the second derivative of position. So r prime of t is double prime, I don't know. And once again, it's just taking a derivative, like it's just taking a derivative of a vector function where you're taking the derivative of each component, and that gives us the new, like for example, x component, right? We take the derivative of the x component to get the new x component for our derivative function. So 2 I hat, the derivative of a constant 0, so I wouldn't include like a j hat term. I will, or no, it's fine. 2 I hat and then plus negative 1 over t squared k hat. So that's acceleration. Not too bad, right? These are just using the definitions of what we know about what velocity means. It's the rate at which position changes with respect to time. That would be just taking the derivative with respect to time. And visually, if you think about, well, what does velocity really mean? Or in this case, like velocity is just r prime of t, which is just taking the limit as h approaches 0 of r prime of t plus h minus r prime of t all over h, right? This is just the definition of a derivative, and it's a useful definition in this case just to kind of see, because you can imagine if this was r, right, so let's do it like this. If this was our r prime, or r of t plus h, right? Then this quantity, r of t plus h, where t plus h, right, h is just some time forward compared to t, right? So it's going to be a little bit forward in the curve, but if I take r of t plus h minus r of t, that's just vector subtraction. So I end up getting this vector right here, right? When I flip r of t, no, not flip r of t. Oh yeah, when I flip r of t, put it here, tip to tail, I get this vector right here. And this is my subtraction vector. And as h approaches 0, as this difference in r of t, right, as the h approaches 0, you can see that this is my new, right, this right here is my new subtracted vector. And then as I get closer and closer, it's been kind of hard to tell, but that velocity vector ends up converging to this right here, right, when you take the limit. But more specifically, you can see visually it's tangent to the curve, right? So that's just another thing to think about, is that, yeah, my velocity, so this is just This is just the difference, right? And when I divide it by a really small number, I will get some velocity vector like so. And it's going to be tangent to the curve. So that's just one thing I want you guys just to understand visually, right? Like visually, that's what velocity looks like. It's tangent to the curve. Now, how do you find the speed? Well, speed is just the magnitude of velocity, right? So to find the magnitude of any vector function, I'm just taking the square root and adding up the squares of all the components, right? It's Pythagorean theorem. It's how we find the vector, or the magnitude of any vector. So the magnitude of v of t is going to equal 2t squared plus 2 squared plus 1 over t squared. And I have like 4t, so when I square this out, 4t squared plus 4 plus 1 over t squared, right? This could be its function itself. You can actually clean this up. A little trick you can do here is factor out a 4 over t squared, which is a little like, what? That's a weird thing to factor out. But this is actually, this is an algebra trick. If you ever see like you have a t squared term or like an x squared term, right? If you have some term squared and the term isn't here, so it's, and in this case it's t to the 0th, right? Because you don't see it, so it's like multiplied by 1. And you have a t to the really negative 2, right? Because it's 1 over t squared, so t to the negative 2. You can factor out like a t squared here, and I'm ended up with t squared plus, so in this case, if I factor out a 4 over t squared here, this would end up becoming t to the 4th, right? Because when I multiply it back, I'm back to 4, oh my god, 4t squared, there we go. So t to the 4th, same thing here, this just becomes t squared. When I multiply it back, I get 4, because I'm really dividing, or not dividing. Yeah, I guess I am dividing by this when you divide. Yeah, whatever, you don't need to really think of it like that. It's more like when I multiply this back, I get back to 4. And then here, this becomes 1/4, right? Now, the reason I did this is because what we can kind of do is we can actually, this can be expressed as a binomial, right? You can actually kind of, first of all, you can take this out of the square root. I get absolute value of 2 over t here. And then for the square root part, this is actually binomial where instead of a traditional binomial like x squared minus 7x plus 6, I don't know if that's a binomial actually, but for a traditional binomial you have like x squared plus 2x plus 1, instead of like x, it's t squared. So you have like t squared squared, right? You have this t squared squared plus t squared plus 1/4. So it's like I can express this as a binomial because it's like the t squared term. If that kind of makes sense, I can show you when I actually factor this out, or not factor, I guess factor. This ends up becoming t squared plus 1/2. You could see that when I square this binomial here, I end up getting my t4th term. You would do 2 times t squared times 1/2. For the middle term, that just ends up being t squared, and then I just square the last term, which ends up being 1/4. So that's a really quick way I can kind of cancel out this square and the square root. I end up getting, for my speed function, ends up just being equal to the absolute value of 2 over t, or I guess absolute value of this whole thing. Yeah. It ends up just being absolute value of t squared and 2 over t times t squared plus 1/2 squared. Jesus, that's a mouthful. Or I guess this is like this ends up being absolute value. Okay, there we go. You don't need to worry too much about that algebra. But this is just to show you, how we can relate all those things. So now what we can talk about is acceleration. So what we can kind of prove, or I guess we can kind of show is that, well, hey, if you had a vector function, let's just say we have a vector function. We're going to look at 2D here just because it's, it's, you'll see in a second. We have a function, or not a function, but let's say like an object is moving in some way in a circle, like so. Just pretend it's centered. Okay, maybe I could do a better job of drawing this. But let's say we have an object moving in a circle and it's moving at a constant speed. So it's moving in this circle at a constant speed. So what does that mean? Well, that just means your velocity. So this is your position vector right here. Your velocity vector looks something like this, right? It's tangent to the circle at any point, but it's also not changing in speed. So the length of this, the magnitude of this v of t vector, right, the velocity vector, isn't changing. And what you can actually show is that, therefore, the acceleration is always perpendicular, or we can also say it's always perpendicular to the velocity vector, and it's always normal to the curve. And you can actually show this because, let's just take, I'm just going to say, like, if we were to think of v dot v, this would give us the magnitude squared, right? When you take the dot product of a vector itself, you just get that, the magnitude of that vector squared. So I'll just call it v squared without the vector notation. And let's just take the derivative of both sides just for fun, right? If I take the time derivative on both sides, time derivative here, right? It's a constant v. Oh, yeah, it is a constant, yeah, because the speed isn't changing, right? V, we in this case it's not speeding up, slowing down, so it's a constant. This derivative just becomes 0. So now we just do product rule here. So I get v prime dot v plus v prime dot v, right? Because I'm taking the derivative of this times this function plus the derivative of this times this function. Well, it's the same function. I just end up getting v prime dot v plus v prime dot v. What is v prime dot v? That's just the acceleration, right? The rate at which acceleration changes. So I end up getting 2 times v dot a equals 0. And I can actually factor out a 2. This is one of our dot product properties, is that like the dot product of 2 times a vector function dot another function ends up just being the same thing as 2 times the whole dot product. So I can but I can divide both sides by 2, and I get v dot a equals 0. And this tells me that the velocity and the acceleration are always perpendicular. In other words, the acceleration is always normal. So this is just one thing to keep in mind, is like, hey, if the velocity isn't changing, then the acceleration is normal. But if the velocity were changing, what you would find is that, well, the velocity is always changing. Oh my God, I'm so sorry. If the speed is changing, if the magnitude is changing, then what you'll find is, okay, this time derivative of speed squared, it's not going to be 0. It's going to be some function of t. And then what you see is that it would be some function of t, and then you would get v dot a equals some function of t divided by 2, right? But if the speed is changing, that means some component of the acceleration is parallel with the velocity vector function. It's tangent to the curve. So there's going to be, and my whole point with this is, there will be, if the magnitude of velocity is changing, if the velocity itself is changing, there will be components of the acceleration vector that are normal to the curve and tangential to the curve, or parallel to the velocity function, perpendicular to the velocity function. So let's kind of derive that. Let's see if we can kind of figure out what components will end up being what. Now, let's say we have a velocity. So let's say we have a velocity function v of t, right? Sorry, give me one second. I'm just gonna look at my notes. I was gonna kind of derive it by the fly. Okay, yeah. Let's start now. Okay, I just need to remember how I even begin this derivation. So the velocity v of t will always end up being the magnitude v, so this you can think of as speed, right? Speed times the tangent vector the unit tangent vector, right? Because for the unit tangent vector, it's defined as the derivative of the position vector, which is in this case the velocity, over the magnitude of the derivative, which in this case is speed. So we can start with this top bit right here, and then we can take the derivative. So if we take the derivative on both sides, I get a of t, so I'll just write d of t, and I'll write a little arrow down. So if I take the derivative, I get a of t, oh, this is bad. Okay, whatever. We're taking the derivative here. Okay, so a of t is going to equal, now I got to do product rule here. So I got to say, hey, v prime times t of t plus v times t prime of t. Well, what is t prime of t? Well, I know that it's, first of all, I know t prime of t is going to be, it's t prime of t is going to be some scalar multiple, beta, I'll just say beta, of the normal vector, right? The derivative of the tangent vector, the unit tangent vector, is perpendicular to the curve, because its the magnitude of the unit tangent vector doesn't change. So we kind of proved that here, that they would indeed be perpendicular. So it's going to be some scalar multiple of the normal vector. Well, what is the magnitude of t prime of t? So the magnitude of t prime of t is related to the curvature. We know the curvature of a function kappa, I was going to say kava like the restaurant. Kappa is going to equal t, the magnitude of t prime of t over the magnitude of r prime of t. So it's like this kind of ratio where it's like, hey, how much does the unit tangent vector change? How much does the unit tangent vector change as the as like the position changes, if that as the velocity changes. So if like the magnitude, oh my god, as the magnitude of speed, or oh my god. Okay, let me think. Let me get my words down. How much does the magnitude of the unit tangent vector change over compared to how much the position changes, the magnitude at which the position changes, right? I'm just saying that, I'm saying that right. Yeah, wait, oh my god. How much is the magnitude at which the unit tangent vector changes over how much the magnitude of the position changes? That's what curvature is defined as. So I can kind of say, hey, this is really v, by the way. So kappa times v is equal to the magnitude of t prime of t. If I multiply the normal vector by this magnitude, I just get the derivative of the unit tangent vector. So I get t prime of t is going to equal kv times the normal vector. If I sub that back in, I get the acceleration is equal to v prime of the tangent vector times the tangent vector plus kappa v squared times the normal vector. So this actually gives us the tangential components, right? Because this is what's tangent to the curve, and this gives us the normal component. So let's actually think about this for a second. If a particle is moving and its magnitude of velocity changes, meaning its speed changes, there needs to be some component of the acceleration that is tangent to the curve. And if there's any curvature in the path of the object's trajectory, there needs to be a normal component, right? A component perpendicular to the velocity vector, normal to the curve, right? If kappa is 0, that means it's a straight line and it's just speeding up, so there's no component of the acceleration normal to this. When you're actually working with vectors, you're going to find it's kind of weird to find v. Oh my god, I thought that was a spider. Something touched my leg. It was nasty. It was just a wire, though. You're going to be like, wow, finding the rate at which speed changes. If you go back to the last example, right, it was like an absolute value, 2 over t, and you have to take a derivative. That's nasty. You don't want to do that. What you want to do instead is express acceleration, right? This is a good little starting foundation equation, but let's see if we can express this in terms of the position vector, the original position vector of our whatever particle is going through, and see if we can get it in terms of that and its derivatives. So this is kind of a weird way to like go about doing this, but I mean, start here, right? We know that, you know, if we were to do v dot a, it's going to if we were to take its derivative, let me see if I'm going to kind of, do I do this on my own? Should I? Do I do that? Okay, we're just gonna see if I can derive this on the spot. If not, I might cut this out and redo. So you're gonna have they're doing really, okay, let's not actually take the derivative. Okay, I just remembered what I'm trying to do here. In the middle of deriving, I was like, wait, this is what I'm actually trying to do. What I'm doing is I'm doing v dot v prime of t plus kv squared to the normal vector, right? Now, let's say, well, v, what is a velocity vector v? That's just v times the speed times the tangent vector. So v dot, and what I'm going to do now is I'm going to distribute this to the rest of this expression. And you're going to see what I'm trying to do. So when I distribute this over, I get v times v prime time dot. So when I'm doing, okay, this is going to be kind of weird. Well, the magnitude of this, right, because they are both, if you were to think about the dot product equation, they're both parallel. So you're just multiplying the magnitudes of both, which is v and v prime, right, when I distribute the dot product over. And then here, I'm doing vt dot kv squared times the normal vector. Well, these vectors are perpendicular, so the dot product becomes 0. I can actually get rid of this. So I get v dot a is really equal to the velocity multiplied by, or sorry, the speed multiplied by the rate at which speed changes. I just got to divide everything by v. So I essentially get that the component of the acceleration tangent is v dot a over the magnitude v. So the velocity dot the acceleration over the speed. To find the component normal, to find the normal component, I'll just say an. That's not too bad, because what we can do is we can actually use what curvature is. Curvature, the other form for curvature is really v cross a, or in other words, the first derivative of the position vector function cross the second derivative over the magnitude of v cubed. It's pretty crazy. V cubed. The magnitude, so the speed cubed. And in order to get a v, so that's curvature. And if I multiply that by, so if I were to do kv squared, I'm multiplying it by the magnitude of v squared. So that gives us just the speed in the bottom, right? No cube, it kind of cancels out. So for the normal component, I get the magnitude of v cross a over v. And this actually is kind of cool, because what is the dot product? The dot product kind of tells us whether two vectors are parallel to each other and how parallel they are. The more parallel they become, the larger your value of the dot product, because it's cosine, right? And cosine increases as the angle between them gets smaller. And the magnitude of the cross product kind of tells us how perpendicular they are. So as the angle gets bigger, the magnitude of the cross product gets bigger, because the angle, it's like sine theta, right? So as theta increases, so does the magnitude. So the acceleration tangent vectors in terms of the dot product between v and a, which, you know, that's like how parallel they are. So tangent, right, parallel. And normal vector, which is perpendicular, this tells us like the magnitude of the cross product, how perpendicular are v and a. So that's pretty cool connection. I think that's pretty cool. Let's just do an example problem now with all this stuff that we've accumulated. So let's say we had, let me just check my notes for an example problem. Let's say we had a vector function like this. So r of t is equal to t times I hat plus t squared plus j hat times j hat, whoops. And then plus 3t k. Is that the correct vector function? Yep, okay. And let's try to find a tan, and let's try to find a normal. And it's pretty simple, right? Using this kind of form, it's actually not too bad because I just need to find, well, what is the velocity vector? The velocity vector is, it's going to be the derivative. So I hat plus 2t j hat plus 3k hat, and the acceleration is going to equal, this becomes 0, this becomes 0. I end up with just 2j. So then what I can do is I can just take the dot product and the cross product, which cross product's a little weird. It's a little, hard, but I think we can do it. V dot A, if you were to do V dot A, this isn't too bad, right? The x and z components of the acceleration are 0. So when I multiply them with the components of v of t, they just become 0. So really, I'm just doing 2t j hat times this. So I get 4t j hat. So then I just divide it by the magnitude. So, or not j hat, sorry. You're only multiplying the components. But I just I divide this by the magnitude of v, yeah. So v of t, its magnitude is going to equal, so 1 squared plus 4t squared plus 3 squared. I end up getting square root 1 plus, or 10 plus, oh, I did the square already. Whoops, 4t squared. So I end up getting, for a tangent, it's going to equal 4t over square root 4t squared plus 10. Now, for the cross product, if we were to do the cross product, or sorry, for the normal component, like we have to take a cross product. So v cross a is going to equal, now I'm going to do my I hat, j hat, k hat. So for velocity, I have, it's 1, 2t, 3. For acceleration, it's 0, 2, 0. So let's take this cross product. So I'm gonna use a bracket. I like it more. For the x component, I'm doing 2t times 0, that's 0. Minus 3 times 2, that's 6. For the j component, I'm doing 1 times 3, 0. So it just becomes 0 here. Which kind of makes sense. It has to be perpendicular acceleration, so it can't have a component in the j component because it's, yeah, okay, that makes sense. And then for k, it's just 2 here, right? Because it's 1 times 2 is 2, minus 2 times 0, that's 0, so it would end up being 2. Little cross product review. I'm going to take the magnitude, so magnitude of v cross a is going to be square root 36 plus 2, which is going to equal root 40. Or this is also 2 root 10. When I pull out the 4 and take the square root. So this becomes 2 root 10. The normal component, it's the magnitude over v. So 2 root 10 over square root 4t squared plus 10. I can actually, in fact, I can make this just the whole thing is like the square root of 40 over 4t squared plus 10. So yeah, and I could, I guess, I don't really have to factor anything out. I guess I could divide by 2. Doesn't really matter. That has been motion in space, velocity and acceleration. So yeah, thank you for watching. Hopefully I didn't misspeak too much because honestly I was kind of hearing myself like I probably said stuff like v hat. I do that sometimes because the little arrow vector reminds me of it. So yeah, sorry about that, but thank you for watching.